Alright guys, we're finally on our last gas law equation, the ideal gas law. So the ideal gas law deals with ideal gases which technically don't even exist. Um, However, it helps us explain behaviors of real gases. Um, when we talk about ideal gases, there's two uh, basically propositions that it adheres to, which is the gases are perfectly elastic. The gas particles, meaning when they collide into each other, no energy is converted, no energy is lost. That's called perfectly elastic. Um, to me, that's not possible. However, um, as a whole, it can be conserved. That energy can be conserved. Um, but that is something that this ideal gas law adheres to. Another one is the second proposition is that all gas particles neither are attracted nor are repelled from each other. That is the second. So whether that is true or not, we don't know, but it explains physical behaviors of real gases. So it doesn't really matter. It works. It's been tested. It's been experimented. This gas equation is the master key. This is a uh, breakthrough equation. And so here we go. The equation is PV equals nRT. So you remember from all the other equations, P is pressure, V is volume, N is number of moles, and T is temperature. R, however, is your new factor, your new variable. R is called the universal gas constant, or just gas constant. R, the number for R, this you'll have to remember, something to commit to memory here. R is 0. Now, depending on the units here, because this number could actually change if the units are different. So here we go. For these units, this number is 0.0821 atmosphere liter per mole Kelvin. So atmosphere liter per mole Kelvin. Now, how do we get to that number? Well, this is how. If you rearrange your equation to solve for R to get R by itself, you divide both sides by NT. So PV R equals PV over NT. That's how you get R by itself. Now, if you remember standard temperature and pressure, at standard temperature and pressure, 1 mole of gas occupies, so 1 mole of gas at 1 atmosphere of pressure. This is the unit atmosphere. 1 atmosphere of pressure at 0 degrees Celsius or 273 Kelvin occupied. So 1 mole of gas at 1 atmosphere of pressure and 273 Kelvin occupies a volume of 22.4 liters. When you do the math, it gets 0.0821 atmosphere liters mole Kelvin. That's how we get the units. And those units, you have to plug those units into the equation because things cancel each other out during all this. So it's something to remember. Now, sometimes the units can change. If the atmosphere is not atmosphere, it's Pascal or kilopascal. Or if it's not liters, it's milliliters. Or if it's not Kelvin, it's whatever it is. Kelvin, or say they're dealing with Fahrenheit for some reason, you have to convert it over to Kelvin. And so, but the most commonly used units and the most commonly used number for this gas equation, gas constant, is this right here. So here we go. Let's practice using the ideal gas law. All right, here we go. So here's your practice problem. How many moles of a gas at 100 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1.50 atmospheres? So now figure out your variables here. We're looking for how many moles of a gas. So that automatically tells us we're looking for N. So we're searching for N. if we have temperature 100 degrees Celsius, we have our T, we have our 1 liters, which is V, and we have our pressure P at 1.50 atmospheres. So we have all those. You can list those on the side. I listed your gas constant out. Do remember and take the time to memorize this, but I wrote it out for your reference already. You won't see those in practice problems. That won't be given to you on worksheets. It won't be given to you on the test. So you'll have to remember the units and that number. So here we go. We have our pressure here. We have our volume here. We have our temperature here. Always convert to Kelvin, just like Charles' law equations. Convert to Kelvin. You have to convert to Kelvin. If you don't see, if you're looking for N, or say they give you N in the practice problem, so they give you the moles, then you're good, because in the units it's always got to be moles. If they give you mass, like say they give you 60 grams of oxygen at 210 Kelvin, you have to convert that mass to moles. So it always has to be in moles, always has to be in Kelvin. If it's not, convert to it. All right, so here we go. So let's plug in our problem. We're solving for N, the number of moles, so we have to get N by itself. So to get N by itself, all you have to do is divide both sides by RT. Therefore, N equals PV over RT. If you guys struggle with rearranging equations, I can do a whole lesson on just that, a video recording on just that. If you have problems, just let me know. So here we go. This is how we're going to solve for N. PV over RT. And then you're just plugging in your problems. So we know our pressure is 1.50 atmospheres. Volume is 1.00 liters. R is our constant, 0.0821 atmosphere liter per mole Kelvin. Times it by T, it's in Celsius. We have to convert it to Kelvin, so you just add 273. 273 plus 100, 373 Kelvin. And then you work that out. You just multiply the top, divide it by the bottom. We see here that atmospheres cancel out. We see that liters cancel out, all repeatings. Kelvin cancels out. And guess what we're left with? Moles. That's the only non-repeating unit. And what's N? Number of moles. So you did it right. So now, figure out the answer. Take out your calculator. You don't have to multiply by the 1, you know it's the same. So 1.50 divided by 0.0821 times 373. I'm getting 6,814. Let me plug this into the calculator a little differently. So I'm going to actually multiply the bottom first. 0.0821 times 373. So this bottom, when you multiply this, you're just getting 30.6. So let's do 1.50 divided by 1.50 divided by 30.6 equals 0.05 moles. N equals 0.05 moles. So at 100 degrees Celsius, how many moles does it take to fill a 1 liter flask to a pressure of 1.50 atmospheres? It takes 0.05 moles. And this is at standard temperature pressure, so it doesn't matter what the gas is. It could be anything. But whatever it is, it takes 0.05 moles at 100 degrees Celsius, which is 373, to fill 1 liters at a pressure of 1.50 0 atmospheres. Now remember, gas constants at STP. This problem was the STP, but for the gas constant, it was. I know. Little twist there. But that's the ideal gas law. If you guys have struggles with any practice problems, just let me know. We'll work them out on the board. We'll go through them. If not, this is our last gas law equation. So take the time to just practice these over break, memorize your equations, read the last slides on gas effusion and gas diffusion. And that's really it for this chapter. Good job.